Hello, this is video for Mathematics for Game Programmers courses Transforms module. And in this video I will answer these questions. And first I will answer how to define 3D object positions in different coordinate frames. And I will explain these by using this which I found in internet. I will provide link to this page. So I found there's at least 3 different coordinate systems used representing 3D coordinates, and most common is the Cartesian coordinates, which is, I think it's like mostly used, and it covers almost every system, I think. So this Cartesian coordinate is represented by this x, y and z coordinates. We all representing distances from that origin. And the origin may be the world coordinate, or this could be world coordinate or local coordinate, meaning that world coordinate is more static and local is more dynamic. So world coordinate could be like center of Earth, and all points is representing in this coordinate. And the local coordinate system could be more like my arm's positions or gun angle position in my hand, and more like this changeable things. And the local coordinate origin is more changeable from the last point to this new point. Like if I move my arm from left to right, the origin is the 0 point when the arm is in this left position, and this value is the value representing with my arm position in the when I turn it to right. And yeah, there's a cylindrical coordinates, which have also x, y and z axles, but the x and y are representing by this r, both of these, and also there's an angle, and the z coordinate is the same as in Cartesian, representing, like in Cartesian, the x and y are like representing the position on the plane, and the z is the height, how much in the air the point is up or down. So the cylindrical coordinates is like told here. The 0 point is this particular point at that given time, and to get another point, there's the r is this distance from that current point to that destination point, and the theta is the angle representing the direction which way you must go to get that point, and the c is that how much up or down in the air the point is from that current point. But this in most system, like this is used in XNA system, but also virtually all graphical libraries uses these Cartesian coordinates. So these cylindrical coordinates must be converted to those Cartesian coordinates. And it is done by using this. It's rather simple thing to do. It's just to get the Cartesian x, you just make this r times cosine of that angle, and to get y, you get r times sine of that angle, and that set is representing same way as a Cartesian, so there's no need to done any conversions. And also those Cartesian coordinates can be converted in these cylindrical coordinates by this way. Also there's a spherical coordinates, which is kinda same way like this cylindrical coordinate, but these have two angles. And also there's the like this RHO is representing this x and y, and the theta is representing the same, the direct direction from the current point, and the phi is representing the angle, the height angle to that point. And there's also that also needs to be converted to Cartesian coordinates. So it's done by this pi times sine of the I'm not sure about this ensembles, which way it is, but yeah, you can find it out, but it is done this way. So those sine and cosines use those. So this is hopefully answers that first question. Next I will answer how to create transform matrices, and I use Unity for the answer. And here we have this 3D model and transformation matrix of that model's transform values, and this transform matrix represent these values: position, rotation, and scale. And there's also can be represent like sharing of that object, but we focus on these three now. Also, this is a homogeneous coordinate, the matrix in homogeneous coordinate, so that's why that fourth row. But I don't have much knowledge of that at the moment, or how these values consist of forms. All I know that when this value is 1, it means that this 3D vector can be formed from this matrix in that coordinate. And when this value is 0, it means that it can't be represented, or it's not in that coordinate, it's somewhere in infinity, then that location. Or yeah, but we focus on this, like this matrix and these values. And as you can see, this is identify matrix as default when there is no when these are this default start values. And these three first ones represents scale of this object, and when I change these scale values, then those values in that matrix start to change, as you can see, like here. So x scale Y scale and Z scale. And this fourth column represents this position values. First is X, changes. The second is Y, and third is Z. Those changes, as you can see. And this 3x3 submatrix represents rotation. And when then those are added, this matrix becomes a little bit more confusing. So as you can see, there's a pretty decimal values, and this when rotating one value, it affects the other rotation values also. And this comes a little bit messy, and as you can see, the same values for there's a same how you can say the same representing value for scale and rotation. So now I can't be sure how much the Vex scale is when this object is rotated. So it goes mixed up. And yeah, these can be calculated by hand also. There's some formulas like in Wikipedia. There's the formula for calculating rotation. You need these cosines and sines. And also you can calculate reflection by hand. And there's this specified formulas for each values in 3x3 matrix. And yeah, that's hopefully answers shortly for that question. Next I will demonstrate by using Unity the difference of orthographic and perspective projections. So here we have this projection in main camera. It's set to perspective at the moment, and we have the viewing distance. Perspective have the point of view, meaning from which point we are viewing, and the viewing distance also. So if we go put the point of view nearer, it affects the view, the perspective of the view, and then going more distance, it's the object goes more far away. And if we change the orthographic, it's always the same. There is no point of view, there's only viewing distance. So if we goes closer, it doesn't affect at all, and if we go more far away, it doesn't affect the perspective. But as you can see, the object start to disappear because we are reached the maximum point of this distant view. And like distant view is 1000, and if we go to 1005, then the object is all outside of this viewing distance and it can't display it. So that's the quick difference of orthographic and perspective view. Like it said, perspective view have perspective because it have that point of view, and orthographic does not have that point of view, only the viewing distance.